Hello everyone. Welcome to today's presentation on modern C pairs. I'm excited to have you all here as we dive into this fascinating topic. In this session, we'll explore the key features and benefits of modern C pairs, highlight its advancements, and discuss how it can enhance your programming experience. So, let's get started and unlock the potential of modern C pairs together. Now, let's dive into lambda expressions, a powerful feature introduced in C++1.1. Understanding their syntax is crucial as it encompasses four major components that work together seamlessly. First, we have the capture clause. This part allows us to specify which variables from the surrounding scope we want to access within our lambda. It's key to remember that this lets us bring in context, making our lambdas more flexible and useful. Next up is the parameter list here. We define any parameters our lambda will take, much like we would with a regular function. This allows for dynamic input, enabling our lambda to operate on different data. Then, we have the return type. This specifies what type of value, if any, our lambda will return. It's important to explicitly define this when the return type isn't immediately clear, ensuring our lambda behaves as expected. Finally, we have the body of the lambda function. This is where the actual logic resides, what we want our lambda to do with the parameters it receives. So, as we explore lambda expressions further, keep in mind these components and how they contribute to making our coding more efficient and expressive in C pairs. Alright, let's dive into our next topic, which is the capture clause. This is a crucial concept when working with lambdas. So, what exactly is the capture clause? Essentially, it defines how we can access external variables from the surrounding scope within our lambda expressions. This is important because it allows the lambda to interact with variables that are outside of its immediate context. Now, here's where it gets interesting. The capture clause controls how these variables are captured and utilized. There are two main ways that a lambda can capture variables: by reference or by value. Capturing by reference means that the lambda can modify the original variable. This is useful when you want changes made inside the lambda to reflect outside of it as well. On the other hand, capturing by value means that the lambda takes a copy of the variable. In this case, any modifications made inside the lambda won't affect the original variable. Understanding the capture clause is key to effectively using lambdas in your code. It gives you the power to decide how your lambdas interact with their surrounding environment, and this can significantly influence the behavior of your programs. So, as we move forward, keep in mind how the capture clause fits into the overall theme of working with lambdas and functional programming. It's all about flexibility and control in how we manage our data. Now, let's dive into the parameter list for our lambda functions. Just like any regular function, a lambda can accept parameters. This is a crucial aspect because it allows us to pass in values that we want the function to work with. Now, what's interesting is that if your lambda doesn't need to take any parameters, you can simply leave the parentheses empty. This flexibility is one of the reasons why lambda functions are so appealing. They can adapt to various situations based on our needs. Understanding how to effectively use parameters in lambda functions is key as we continue exploring their practical applications. It's all about making our code more efficient and streamlined, which ties back to our overall theme of enhancing productivity and simplifying processes in programming. So, keep this in mind as we move forward. Now let's dive into the concept of return type in lambdas. One of the great features of C++ is that specifying a return type for a lambda is actually optional. This means you don't have to explicitly declare what type of value your lambda will return. If you choose to omit the return type, C++ will automatically deduce it for you, based on the return statement that's inside the lambda itself. This is particularly useful because it simplifies your code and makes it cleaner. You can focus more on the logic of what you're trying to achieve without getting bogged down in type declarations. However, it's important to note that while this automatic deduction is convenient, there might be times when you want to specify the return type explicitly. Doing so can enhance code readability and clarity, especially in complex situations where the return type might not be immediately clear. Overall, understanding the flexibility of return types in lambdas ties back into our broader theme of C++'s adaptability and efficiency. It allows us to write code that is not only effective but also elegant, aligning with the modern programming practices we're aiming to adopt. Now, let's dive into the body of the lambda function. This section is where all the action happens. When the lambda is invoked, the code within this body is executed, and it's crucial to understand how it works. Inside the body, you have the flexibility to use captured variables along with any parameters you've defined. This means you can seamlessly integrate external data and inputs, making your function powerful and adaptable. Think of it as the engine that drives your lambda. It's where you can implement the logic that defines what your function does. So, whether you're performing calculations, manipulating data, or triggering other processes, this is the space where all of that unfolds. Highlighting the captured variables is essential here. They allow your lambda function to access and utilize data from its surrounding environment, which can be incredibly useful for creating dynamic and responsive code. In summary, the body of the lambda is not just a placeholder. It's the heart of your function, enabling you to harness both parameters and external variables effectively. As we move forward in this presentation, keep in mind how this foundational concept connects to the broader theme of leveraging lambda functions to enhance our coding efficiency and capabilities. Now, let's dive into this code snippet. Here we have a simple C++ program. It starts with the standard input-output stream, which is essential for our program to interact with the user. In the main function, we define two integers, x and y, initializing them to 10 and 5, respectively. This is where our numbers are set up for the operation we want to perform. Next, we introduce an important concept called a lambda function. This lambda, named add, takes two integer parameters, a and b, and returns their sum. The syntax here might look a bit new, but it's a powerful feature in C++ that allows us to create functions on the fly, right where we need them. Then, we use this lambda function to calculate the sum of x and y. You'll notice how we call the add function directly, passing our two integers. This compactness is one of the strengths of lambda expressions. They help keep our code clean and focused. Finally, we output the result to the console. However, there's a small mistake here. Instead of std end, it should actually be std endl to properly end the line in the output. This highlights the importance of accuracy in coding. Even small typos can lead to errors. Overall, this example effectively shows how we can define functions dynamically and use them within our code, tying back to our theme of modern programming practices in C++. Now, let's dive into the different capture clause types that we can use in lambda expressions. This is a crucial aspect because it determines how variables are accessed within the lambda. First up, we have the no capture clause. This is straightforward. The Lambda does not capture anything at all. It simply operates independently without any external variable influence. Next, we have by value. Here, we're copying the variable into the Lambda. This means that any modifications we make inside the Lambda won't affect the original variable. Outside. It's a safe way to work with data when we want to ensure the original remains unchanged. On the other hand, with by reference, the Lambda accesses the variable directly. Any changes made within the Lambda will directly affect the original variable. This is powerful, but it requires careful handling to avoid unintended side effects. Now, if we look at all by value, we see that all accessible local variables are captured by value. This is especially useful when we want to ensure that we are working with a snapshot of the current state, preserving the original data. Conversely, all by reference captures all accessible local variables by reference. This means everything is linked to the original variables, allowing for dynamic updates. A more nuanced approach is seen in default by value. Y by reference. Here, we capture everything by value except for the variable y, which is captured by reference. This provides a flexible way to manage how specific variables are treated. Similarly, with default by reference, x by value, we capture everything by reference, except for x, which is captured by value. This mix and match capability lets us fine-tune our Lambda behavior based on our needs. Finally, we have the capture this pointer. This allows us to access class members from within the Lambda. It's essential for maintaining context when we're working with member variables. Understanding these capture types is vital as they significantly influence how our Lambdas interact with the surrounding code. By choosing the appropriate capture type, we can write more effective and safe code, aligning perfectly with our overall theme of enhancing code flexibility and reliability. As we delve into this slide, let's focus on a crucial aspect of Lambda expressions in our programming context. When we see the equal sign followed by this, it signifies that we are capturing all external variables by value. This includes any class member variables that we access through this. Now, capturing this by reference is particularly important. It allows us to interact with the object's current state directly. However, we need to be cautious here. If the Lambda expression is executed after the object has been modified or even destroyed, we can run into undefined behavior. This means that the code might behave unpredictably, leading to potential bugs or crashes. So, to connect this point to our overall theme, it's vital to understand how the lifetime of an object and its members can impact your code's stability and reliability. This understanding is key to harnessing the full power of Lambda expressions while maintaining the integrity of our applications. Let's keep these considerations in mind as we move forward. Now, let's dive into a powerful feature introduced in C++ 1.7 that revolves around capturing variables in Lambdas. We're specifically looking at the capture syntax using this. When we use this in a Lambda, it captures all external variables by value, and that includes the entire object itself. This is significant because it ensures that all class members are copied into the Lambda. The result? The Lambda becomes entirely self-contained. This self-containment is crucial, especially in asynchronous programming. Imagine you have a scenario where your Lambda might outlive the original object it references. By capturing this, you no longer have to worry about the original object's lifetime affecting the Lambda's execution. This feature is particularly useful when you need to create lambda expressions that can safely run in a different thread or context without the risk of dangling references. In essence, it provides a safeguard for your code, ensuring that your lambdas can operate independently and reliably. So, as we wrap up this slide, remember that using this not only enhances the safety of your lambdas but also aligns with our overall theme of writing cleaner, more robust C++ code. Now, let's dive into the final slide, which showcases a fascinating example of lambda expressions in C++. Here we have a class named myClass. Within this class, we have an integer variable, x, initialized to 42. The real magic happens in the example function. First, we define two lambda functions, lambda1 and lambda2. Both of these lambdas capture the context in ways that might seem similar but lead to different behaviors. Lambda1 captures by value, using the this is pointer to access the member variable, x. So when we call lambda1, it outputs the current value of x, which is 42. On the other hand, lambda2 also captures by value but uses a slightly different syntax, which creates a copy of x. When we call lambda2, it also outputs 42. Now, here's where it gets interesting. After calling both lambdas, we modify x to 100. When we call lambda1 again, it reflects this change because it accesses x through the this is pointer, showing us the updated value. However, when we call lambda2 once more, it still shows 42. This is because lambda2 holds a copy of the value from when it was created, which didn't change with the update. The output we see at the end illustrates this perfectly. Both lambdas initially display 42. But after the update, lambda1 shows 100 while lambda2 remains stuck at 42. This example not only highlights the power of lambda functions in C++, but also emphasizes the importance of understanding how different capture methods work. It connects back to our overall theme of mastery in C++ by showing how nuanced the behavior of lambdas can be. Thank you for your attention throughout this presentation.